Hello dear, welcome to today's lesson on the topic position, distance, and displacement. In today's lesson, we shall be looking at the meaning of position, the Cartesian plane and its properties, how to locate points on the Cartesian plane, and also the differences between distance and displacement. What do we understand by position? This is defined as the location of a point in a plane with reference to a given point, and this reference is called a frame of reference. In dealing with position, we have what is called the Cartesian plane, and it has the x and the y axis. And we shall look at this using a video to
What we're
illustrate.
going to do in this video is think about different ways to represent how position can change over time. So one of the more basic ways is through a table. For example, right over here in the left column I have time, maybe it's in seconds, and in the right column I have position. And this could be in some units. Let's say it's in meters. So at time 0, we're at 3. After 1 second, we are still at 3. After 2 seconds, we're at -1. Then after 3 seconds, we're at 0. After 4 seconds, we're at 0. Still at 0. After 5 seconds, we are at 2, maybe 2 meters. Now, this is somewhat useful, but it's a little bit difficult to visualize. And it also doesn't tell us what's happening in between these moments. What's happening at time half of a second? Did we just not move? Did our position just not change? Or did it change and then it got back to where it originally was after 1 second? We don't know when we look at a table like this. But another way to think about it would be some type of animation. For example, let's say we have our number line, and let's say the object that's moving is a lemon. And so at time 0, it starts at position 3, so that's where it is right now. And let's see if we can animate it. I'm just going to try to count off 5 seconds and move the lemon accordingly to what we see on this position time table or time position table. 0, 1, 2, 3, 4, 5. So that was somewhat useful. But maybe an even more useful thing would be to graph this somehow so that we don't have to keep looking at animation, so that we can just look at with our eyes what happens over time. So for that, we can construct what's known as a position time graph. Typically, time is on your horizontal axis and position is on your vertical axis. So let's think about this a little bit. So at time equals 0, our position is at 3. So at time 0, our position is at 3. And then at time equal 1, we're at 3 again. At time 2, we are at -1. At time 2, our position is -1. At time 3, our position is 0. So our position is 0. Remember, even though we're thinking about left, right here, here position is up, down. So here our position is 0 at time 3. And then at time 4, our position is still 0. And then at time 5, our position is at 2. Our position is at 2. So for the first second, I don't have a change in position, or at least that's what I assumed when I animated the lemon. And then as I go from the first second to the second second, my position went from 3 to -1, from 3 to -1. And if we do that at a constant rate, we would have a line that looks something like this. That's supposed to be a straight line. And then from time 2 to 3, we go from position -1 to 0, from -1 to 0. Here, it would have been going from -1 to 0, moving 1 to the right. But over here, since we're plotting our position on the vertical axis, it looks like we went up. But this is really just going from position -1 to position 0 from time 2 seconds to 3 seconds. Now from 3 to 4, at least the way I depicted it, our position does not change. And then from time 4 to 5, our position goes from 0 to 2, from 0 to 2. And so what I have constructed here is known as a position time graph. And from this, without an animation, you can immediately get an understanding of how the thing's position has changed over time. So let's do the animation one more time and just try to follow along on the position time graph. And maybe I'll slow it down a little bit. So over the first second, we're going to be stationary. So we could just count off 1 Mississippi. And then we go to, our position goes to -1 over the next second. So then we would go 2 Mississippi. And then we would go 3 Mississippi, 4 Mississippi, and then 5 Mississippi. But hopefully you get an appreciation that this is just a way of immediately glancing and seeing what's happening.
That was the video on position. Let's talk about distance. Distance is simply how far a body has traveled without reference to its direction. For example, a body travels 8 kilometers, that's distance. It may be in 15 minutes, 10 minutes, as the case may be, without a specified direction. But when we talk about displacement, we say displacement is simply distance traveled in a specified direction, talking about the magnitude of that body and its direction. But take note that there is a distinct term between distance and displacement. Why? Because distance is simply the movement of a body probably from one point in space to another without reference to its direction. But displacement, on the other hand, talks about the direction that body is moving to. Let's take, for example, a body traveling from point A to B. That body is said to start from point A with 5 kilometers. It moves round down to 3 kilometers and then move down to another 5 kilometers and therefore comes to the end point. So to calculate the total distance traveled by that body, it becomes the addition of 5 kilometers plus 3 kilometers plus another 5 kilometers to give you a total of 13 kilometers. Let's see another example. When you consider a person traveling from point A to B, you see that the total distance traveled there is 16 meters. So this now gives you a distance between distance and displacement, which shows that distance is simply a total path traveled by a body, while on the other hand, displacement talks about the direction in which it travels. Let's watch this video. Hello students, welcome to my class on acceleration, displacement, and average velocity time graph. You have to take note that on a graph there are two axes, which we have the y-axis and the s-axis. Particularly this graph, it is noted that the y-axis carries the velocity, which is measured in meter per seconds, and the x-axis carries the time, which is measured in seconds. A straight diagonal line going up from left to right represents a constant acceleration. And take note that the steeper the line, the greater the acceleration. The horizontal line represents a constant velocity, and a straight diagonal line which goes from left to right represents the deceleration or negative acceleration. If the object has the same decrease in velocity over a short time, like this, the deceleration will be greater. Now look at a graph showing the velocity ranging from 0 to 3 meters per second and a time interval of 0 to 10 seconds. Come again, look at the graph showing the velocity ranging from 0 to 3 meters per second and a time interval between 0 to 10 seconds. We note that during the first 2 seconds, we observe a constant acceleration, which can be calculated using the formula A is equal to V minus U all over T, where U is the initial velocity, V is the final velocity, and T is the time taken for the velocity. So, when we consider the first section where we have a velocity of 2 meters per second and a time of 2 seconds, our acceleration becomes 1 meters per second for the first 2 seconds. In the next section, we'll have a constant velocity of 2 meters per second, while the time taken is 4 seconds, which is from 2 seconds to 6 seconds. When we substitute these values into the equation, we will get 2 minus 2 over 4, which gives us a total of 0 meters per second square. In the third section, which is a constant deceleration, the initial velocity uses 2 meters per second, while the final velocity is 0 meters per second. The time taken is 3 seconds, which is from 6 to 9 seconds. When we substitute these values into the formula, we will get a value which is 0 minus 2 all over 3, which gives us a negative 0.67 meters per second square, or 0.67 meters per second square deceleration. So therefore, to get the displacement of a velocity time graph, we need to first find the area under the graph. You have to take note that this will comprise 3 sections, which we have 2 triangles and a rectangle. For the triangle, the formula to calculate that gives us half base times height. So the area of the triangle for the first part will get a substitution of 0.5 times 2 times 2. For the second part, which is the rectangle, it is base times height. The base we have 2 to 6 seconds, and the height we have 2 meters. Then for the third part, we'd have another triangle which gives us half base times height. You convert the half to 0.5 and you substitute into the values, you get 0.5 times 3 times 2. By summation, when you add these 3 values together, you arrive at a total answer of 13 meters for a displacement. Next, we shall be looking at a calculation on average velocity, which has a formula which is velocity is equal to displacement over time, where we recall that we had a displacement of 13 meters. When you substitute with a total time of 9 seconds, we'll arrive at an average velocity of 1.44 meters per second. Take note that this is what the object requires to travel an equal distance in the same amount of time. To find the displacement of a graph which has a straight or a slight change as you see in the graph, it will now be divided into 4 sections. There we have 2 triangles and 2 rectangles. In the first case, we said we already seen the previous displacement, how to calculate it, the various sections. It's just the last part. You now consider the triangle, triangle which is from 2 to 1, and that will be calculated with 0.5 times 3 times 1. Then you add it to the rectangle 3 times 1, which gives you a total answer of 14.5 meters. 14.5 meters. Just before we conclude this lesson, you have to take note that for solving of the velocity time graph, you have to be careful while reading questions on displacement, as sometimes you might be given questions to calculate the displacement of an incomplete graph. In that case, you would have to look for the triangle, the rectangle, a little triangle at the curve, and a rectangle. With this, I round up today's class. I want you to attempt the question above. What do you think is the displacement from A to C? Of course, the answer is 5 meters. That's very correct. With this, we've come to the end of today's lesson. I want you to attempt your quizzes and take your assignment session very serious. Till we meet in our next class, do have a wonderful day and bye for now.